All right, let's get to it. Limits and differential calculus day number 2. Our topics for today are the squeeze theorem, which is a new method for evaluating limits, the definition of continuity, the types of discontinuities, and then what's called the intermediate value theorem. So let's go ahead and get started. Okay, so indeterminate form method number 5. So the first few forms we had were factor reduce, we had conjugate reduce, we had clear fraction, and we had divide by the largest power, right, which typically took place with polynomials, but could be with other situations too, depending on that. The fifth method we've got here today is the squeeze theorem. So I want to go over the general concept of the squeeze theorem over here first in this area. Let's say that you're taking the limit as x approaches a of g of x, and it is bothering you big time. And one of these other methods, the first 4 methods, is just not working for you. Well, what we can do is if we can find a function f of x that's always less than g of x, and h of x, which is always greater than g of x, then we can do what's called squeezing it if both the limit as x approaches a of f of x and the limit as x approaches a of h of x are the same. So in essence, what you're doing is both of those are headed to the same y value as x approaches a certain value, in this case a. So it must then squeeze g of x in order to also follow suit if it's going to be between those two values. So we could then say that the limit as x approaches a of g of x would have to be 2 by the squeeze theorem. Okay, we're going to do that with this special limit right here. And this special limit is kind of cool. I mean, if we were to try to directly evaluate this, we would plug in 0, we'd get sine of 0 over 0, which is the indeterminate form 0 over 0, right? Which means to us there's more work to do. Now, it's possible that the limit would not exist, or that it's 0, or that it's some finite number, right? But we don't know what that is. So here's how we go ahead and we work through this limit. It's a pretty cool proof. Okay, I'm going to show you the proof to this limit here right now. So I take the unit circle in quadrant 1. Okay, so this would be the point 1, 0. This would be the point 0, 1. And let's pick a point out here. Let's call it x sine x. All right, so I'm gonna sketch that as well as this dotted line here. Okay, so the dotted line represents sine x. This length right here represents cosine x, right, if we're in the unit circle, which has a radius of 1. And this angle right here is x. Okay, that's cool. All right, so that dotted length, I'm gonna actually put it in, let's put it in red. All right, so that's sine x, that length, okay? Now this arc measure here, I think we can agree as this point x sine x approaches, so if this angle approaches 0, right, like we're doing here, approaches 0, the green length will always be longer than the red length, which is true. Okay, that green length is an arc length, and we know that arc length s equals r theta. Now in this case theta we're calling x, and r is 1. So that arc length is actually just x. Okay, now I'm going to draw a triangle. Another triangle, it's tangent to the circle. Okay, and I'm going to extend this triangle out like this. That blue length, I think we can agree, as the angle x approaches 0 would always be greater than the green length, and the green length would be greater than the red length. Okay, this blue length is actually equal to the tangent of x, and I'll show you why here in just a second. Okay, so let me sketch each of these 3 scenarios. Here was 1, and then we had sine x, and here's x, and in the sector case, same situation, there's x, and There's x. Let's call this sine x. Okay, and in the third case, I have this length of 1. I have a 90-degree angle here. And this is x as well. Okay, so let me show you how it is that I come up with tangent. And of course, if you're not interested in this right now, you can skip ahead and see what the limit equals. I'm going to call this y for just a second. Okay, using geometry, I know that if I have angle-angle similarity, which I have an x and a 90 here, x and a 90, this side next to, adjacent to x, should be proportional. So cosine is proportional to 1, as the other leg, sine, is proportional to y. So let me write this out. So cosine is proportional to 1 in the same way that sine is proportional to y. Now if I were to solve for y, I end up getting sine x over cosine x, which is tangent. So y is equal to tangent x. Okay, now this is where the fun part comes. Right, what's my goal in all this? And my goal is I want to find the limit as x goes to 0 of sine x over cosine, or excuse me, sine x over x. I don't know what that is. I want to find out. So I know this though. I know that sine x will always be less than x, which is always less than tangent x. All right, so how do I get this in a form that I'd like? All right, well, the trick here is actually I'm going to divide everything by sine x. All right, sine x, sine x, sine x. All right, what I end up getting is 1 is less than x over sine x is less than, if you divide tangent by sine, you actually get 1 over cosine. You could write that as secant, but it's not really that helpful. Okay, so I get this. Cool. Well, I see kind of what I'm looking for here. So I'm going to actually flip this. I'm going to reciprocate. And when you reciprocate, the inequality is going to flip. That means now instead of being less than 1 over cosine x, when I flip it, that'll become cosine x, means it's greater than cosine x and less than the reciprocal of 1, which is still 1. Okay, so this is cool. This is the squeeze theorem, right? I've got a function. We said if f of x is less than g of x is less than h of x, and both f and h go to a certain value, then g is forced to go to that value. So I'm going to show here now that if x goes to 0 of cosine x, well, what's that? That's cosine of 0, which is 1. And the limit as x goes to 0 of the number 1, right? So if x goes to 0, it doesn't matter. 1 never changes. That's also 1. Then by the squeeze theorem, I would write out squeeze theorem if I were you. IB may not know your abbreviations. That could mean straight. I don't even know. I was gonna try to do something with push-ups or pull-ups. I don't know. Oh yeah, strong triceps. That's what it is. Okay. Sine of x over x is going to be forced then to go to 1. So that's a cool limit. 0 over 0 actually equals 1. That's cool. Let's use it on the next slide. Okay, now we have access to this limit. And a reminder, the limit as x approaches 0 of sine x over x is equal to 1. Okay, so how can I use that in these scenarios? I don't see sine x over x, right? Especially in this first example on the left, right? So what I'm going to do is first I'm going to evaluate. I know I'm going to that special limit, but let's evaluate anyways. As x goes to 0, x would be 0, and cotangent actually goes to infinity. That's weird. That's a new indeterminate form. Let's throw that in our toolbox of indeterminate forms. Okay, but that's actually going to equal a number. And let's see what that would equal. Well, I'm going to write cotangent in terms of sine and cosine. So this would be limit as x goes to 0 of x times cosine x over sine x. And if you remember back, I think it was last lesson, yeah, we have this product rule of limits. We're allowed to do this. I'm going to take the limit as x approaches 0 of x over sine x times the limit as x approaches 0 of cosine x. Okay, well, I know that the limit as x approaches 0 of cosine x is 1. And the cool thing about any limit that equals 1, like for example, our limit here, the limit as x approaches 0 of x over sine x or sine x over x is going to be the same because 1 is its own reciprocal. So that will also equal 1. And therefore, 0 times infinity actually equals 1. That's pretty cool. Okay, let's look at the second example. Boy, I don't have the ability like I did in the first question to manipulate using trig, but what I can do is I can multiply by 1. So I'm going to multiply by 1 by multiplying the top and the bottom by 1 over x. When I do that, I get the limit as x approaches 0 of x over x plus sine x over x over x over x minus sine x over x. Okay, so you can visualize this as one big limit, and you don't need to split it up using those properties at all times. It's just sometimes nice to see it happen that way. But I'm going to get 1 minus sine x over x over 1 plus sine x over x over 1 minus sine x over x. Well, we know that the limit as x approaches 0 of sine x over x equals 1. So I have 1 plus 1 over 1 minus 1, which is 2 over 0. And when I get a number over 0, I'm happy with that, not because I want it to exist, because this limit actually does not exist, but because it is a definitive answer. We know for sure it doesn't exist. Okay, very good. Let's keep moving and talk about some continuity. All right, so the definition of continuity, f of x is continuous if the limit as x approaches a of f of x actually equals the value f of a. All right, so f of a has to exist. The limit must exist, which means that the two-sided limits on both sides match up, and the limit must equal the value. So this is what this means. Okay, a value has to exist. So f of a has got to exist. And coming from the left, it's got to equal coming from the right. So continuity just means you never have to pick up your pen when you're drawing the function. Okay, so let's look at example 1. Evaluate the following limits and determine if f of x is continuous at x equals 1. Okay, so the limit as x approaches 1 from the left of f of x, let's see what it is. As we approach 1, come in here, our function value will equal 1. Okay, coming from the right, looks like it equals 3. That's going to be a problem with continuity. Right? Therefore, the limit as x approaches 1 of f of x does not exist, right? Because 1 and 3 don't match up. All right, f of 1 is 1. We can see that we got the filled in bubble here, and we got a hole here. Right? This is called a jump discontinuity. It jumps from one location to another. All right, so clearly f of x is not continuous. Not continuous for multiple violations, right? So but we could specifically say just in one way that the limit as x approaches 1 of f of x does not equal f of 1. All right, f of 1 is 1 and the limit doesn't exist, therefore we got problems. Okay, let's look at the types of discontinuities. All right, there are 3 types: removable, jump, and essential. So essential are anywhere there's a vertical asymptote, right? So we've got an essential discontinuity here at, it looks like x equals 0. There's a problem. I got to pick up my pen to go from over here to over here, right? That's an issue. So we've got an essential discontinuity or a vertical asymptote at x equals 0. Okay, there are other places that we've got discontinuities. Here's a discontinuity, and it's very similar in nature to there. Okay, that's called a jump discontinuity. So I've got a jump discontinuity where the graph jumps to a different limit from its left-sided limit to its right-sided limit. So jump discontinuities at x equals -2 and x equals 4. All right, and then we've got one more discontinuity. This is actually interesting. The limit exists there, but the function's not continuous. So we have a removable discontinuity, though there is no actual value for f of 2. But this is called a removable discontinuity. Sometimes it'll show up with that value showing up somewhere else, but at x equals 2. Okay, those are the three types of discontinuities. Let's talk a little bit more about continuity on the next slide. Okay, using the definition of continuity, find the value or values of k for which f of x is continuous. Okay, so there's clearly a line that's meeting up with a quadratic. What value for k would make the line meet the quadratic at x equals 2? All right, so what I need to do is I need to take the limit as x approaches 2 from the left of f of x, which I know will be k plus 1, right? Because there's no independent variable to plug in at 2. Okay, so I know that's the left-sided limit. I need to know the limit as x approaches 2 from the right of f of x, which will be 2 squared, which is 4. And I need to know f of 2. And f of 2 actually we found with that right-sided limit, which will be 4. Okay, so I want the left-sided limit to match the right-sided limit. That means I want k plus 1 to equal 4. And the only way that can happen is if k equals 3. And there you have it. That value for k would make the function continuous at x equals 2. All right, let's look at number B. Number B. Cool. Okay, now we don't have a piecewise function that gives us a left side of the function and a right side of the function. We just have a situation that looks like it potentially could be a jump discontinuity. So sine of 3x over x might look like this. I don't know. And then k is just some value. Okay, and apparently I'm crazy, but all right, let's say sine of 3x over x is that. And then at x equals 0, we want to plug this gap. Whatever that gap is, I want to plug it. So I have to find a value for k such that I can bridge that gap. Because clearly, if I plug in 0, right, if I take the limit as x approaches 0 of sine of 3x over x, and I plug in a 0, I'm going to get some issues there, right? Which likely means there's some kind of discontinuity going on there, likely a hole. Okay, so we're going to plug that hole with a value k. So I have to evaluate this limit, sine of 3x over x. Okay, and here's how you do that. I'm going to multiply by 1 by multiplying by 3 over 3. So look what that does to this limit. That takes, and it makes 3 sine of 3x over 3x. All right, and just for a moment, I'm going to do a quick substitution. I'm going to say u equals 3x. So what we'll get here is I'm going to rewrite my limit in terms of u. So as x goes to 0, what would u go to? U would also go to 0. Okay, so as u goes to 0, we would have 3, I'm going to sub in a u for 3x, sine of u over u. Now that looks great, right? I'm going to use a property of limits where I can take a constant out. And I have the limit as u approaches 0 of sine of u over u, which should be 1, you guys. Doesn't matter the variable. Now, a little shortcut. If you ever see anything like this, where you have sine of something over that same thing, you can consider that limit 1 from here on out. okay? And then you just take, of course, 3 times that limit, which comes out to be 1, and you get 3, okay? Very good. We got one more slide here on intermediate value theorem, and then we'll be done for day 2. Okay, the intermediate value theorem. I'm going to draw a chicken. It's going to be a bad chicken. Not like it's a misbehaving chicken. It's just probably not going to be the best chicken ever that you've ever seen. Here it's large talons. That's not a Napoleon Dynamite reference, or maybe it is. Okay, there's our chicken. Okay, I like to think of the intermediate value theorem as the chicken crossing the road. It can't teleport, and you'll see why in a second here. So suppose a function is continuous on a closed interval from a to b. Then there exists a value c within a and b such that f of c is between f of a and f of b. So check it out. Here's a, here's b. Here's f of a, here's f of b. Now, it could be the other way around, right? I could have, here's a, here's b, here's f of a, and f of b is, depending on if the function is increasing or decreasing, right? So if the function is increasing, and it's continuous, right? I don't care what it looks like. It could look like that. It could look like that. I don't care. Right? If I pick a value in between, c, that value, that output for that value, okay, f of c, we're guaranteed that f of c, there will be at least one value in between those two, okay, in between those two. So basically, why did I reference the chicken? Well, the chicken wants to cross the road and wants to go over here to the workout facility to do some chicken gains. Okay, and it's got to go across the road. That means it has to touch every part of the road. Okay, or at least its body has to pass over every part of the road. All right, so using the intermediate value theorem, the key is the function must be continuous. Okay. So let's look at a couple of examples using the intermediate value theorem. So example number 1, explain using IVT why f of x must equal 3/4 on the interval from 0 to pi over 2. Well, the first thing that you can note is that sine and cosine are always continuous. So f of x equals sine x is continuous on the interval from 0 to pi over 2. Okay, the next thing you want to do is you want to find f of 0, which sine of 0 is 0, and f of pi over 2, which is equal to 1. Therefore, by the intermediate value theorem, we're guaranteed that f of x will hit every value in between. Thus, there exists a value c between 0 and 1 such that f of c equals 3/4. Okay, I forgot to say thus by the intermediate value theorem. There exists a value c between 0 and 1 such that f of c must equal 3/4. Okay. Looking at the last example, you guys, you know, you can get fooled once in a while, but in this case, we know that, and it's giving us our answer, but using IVT, explain why g of x cannot equal 0. Well, the reason why is because g of x is not continuous on the interval from -1 to 1. Okay, g of x has a vertical asymptote there at x equals 0. But some might get fooled and think, well, g of -1 equals -1, and g of +1 equals 1, and therefore somewhere in between it's got to hit 0. Well, we know the graph of 1 over x looks like this, with horizontal asymptote here, vertical asymptote here. So even though g of 1 is a positive 1 and g of negative 1 is a negative 1, we got that issue in between. Okay, that's it for today. We went over the squeeze theorem, we went over continuity, and we also went over the intermediate value theorem and what that means for continuous functions. So hope that made sense. We'll see you in the next video. Have a great day.